Hey guys, in this video we're going to be wrapping up section 3.2, talking about variation, and we're going to talk about a specific theorem called Chebyshev's theorem. Now, pronouncing that name is a little bit challenging, and I, of course, probably did not do that right. So I do have a pronunciation of this guy who invented the theorem we're going to talk about today. Here it is, Pafnuty Lvovich Chebyshev.
Pafnuty Lvovich Chebyshev.
There you go. He is Russian. He came up with this theorem that allows us to make statements about how much of, if we have a sample of data, how much of the population of the data would fall into a certain interval. So it's an important theorem. We'll see a similar one called the empirical rule in coming sections, but this one is particularly good because it works for any distribution of data. The empirical rule, which we'll see in the future, is only good for if we have symmetric data, but this is actually good for anything. So what this theorem states is that for any data set and for any constant, we're going to call k, greater than 1, so that means like 2 or 3 or 4, something like that, the proportion of the data that must lie within k standard deviations on either side of the mean is at least, it's given by this formula. 1 minus 1 over k squared. All right, I know it's a lot of words. Let me try to explain it. So let's say we have our k equals 2, meaning we want to know how much, sorry, I'm going to spell much, how much of the data is within 2 standard deviations of the mean. Now what I mean by that is, let's say our mean is 50, okay, and our standard deviation is 5. Okay. So how much of the data was within 2 standard deviations of the mean? What I mean by that is, if we were to take the standard deviation and add it twice, plus 5, that gives me 60. And if I were to subtract it twice, minus 5, I would get 40. So this interval 40 to 60, that would be within 2 standard deviations of the mean. Okay, so how much of the data would be in that interval? Would we expect to be in that interval? So what you do is use this little formula, 1 minus 1 over k squared. So 2 is our k, because we're 2 standard deviations of the mean, times 100. And what we end up with is 1 minus 1/4 times 100. Well, that's equivalent to 0.75 times 100, which is 75%. So we can say that if we had some study and the mean was 50, standard deviation was 5, we could say that 75% of the data is within the interval 40 to 60. Now you could do one better if you want to say 3 standard deviations of the mean. So if I subtracted another 5 and made this 35 and then made this 65, and then I made my k3, it'd be 1 minus 1 over 3 squared times 100. And so that would become 1 minus 1/9. 1 minus 1/9. 0.888. So this would be 88.9% of the data would be within 3 standard deviations. And I can continue this pattern more and more and more to find whatever interval I'm looking for. So that's what we're going to apply here. The more practical application and how we're going to use this Chebyshev's theorem is this slide. So you might want to even take a picture of this. Based on what I just did, we can say that at least 75% of the data fall in the interval. And this one is particularly talking about population, but it's the same for sample. So this would be x bar plus or minus 2s. Remember, those symbols are the same whether we're talking about population or sample. So we can say at least 75% of the data fall in the interval mu plus or minus 2 sigma, or x bar plus or minus 2s. In other words, the mean plus or minus 2 times the standard deviation. And then if we were to continue this further, what I just proved was 88.9% for 3 standard deviations of the mean. And again, this could be x bar plus or minus 3s. And then if I were to take that up to 4, if I were to do my little formula, I'd get 93.8. So it'd be the same thing as x bar plus or minus 4s. And we're actually going to just use that x bar and s most of the time. And then for 96%, that would be within 5 standard deviations of the mean. So x bar plus or minus 5s. And here's a little graphical picture. You can kind of see what's happening. If this blue represents the distribution of our data, we could say that 75% is between those two green lines there. X minus 2s and sorry, x bar minus 2s and x bar plus 2s. And then we could just sort of continue this out. If I had 3 standard deviations of the mean, it'd be out here somewhere. It's not a very straight line. And then we would say at least 93.8% would be within that 4 standard deviations of the mean, and that could go further, 96%. And you could even continue this further and further until it was virtually 100% of the data. So that's how that's what the theorem is. Let's look at some applications of how we're going to use this. So our first question, we went to a soccer game, and the average age of the parents at the soccer game was approximately 34.5 years old. The standard deviation of this sample was 4.5. So in what interval must 75% of the data lie? In other words, what could we confidently say at least 75% of the parents are this age range? So essentially what we're saying. Well, 75%, if we look back, that corresponds to 2 standard deviations. So all we're going to do is just do 34.5 minus 2 times our s, and 34.5 plus 2 times our s. So that becomes 43.5. I'm sorry. That was actually the plus, sorry. So that'd be minus 9, which would be actually, 25.5. And then if we added it, it would be 43.5. So we could say that 75% of the data, meaning 75% of the parents' ages, are between 43.5 and 43.5 years old. So hopefully that kind of makes sense. We'll look at a couple more examples. But again, basically what you're trying to do is figure out, given that number, 75%, you're just going to match that up. How many times do I need to add and subtract the standard deviation? You just add 2 times the standard deviation, subtract 2 times the standard deviation, and that gives you some interval, and you can interpret what that means. Again, this means that 75% of the parents at the soccer game are between ages 25.5 to 43.5. Let's look at another one. Right. So a newspaper has an average of 525 responses per advertisement, and the standard deviation of this study is 30. So we're going to determine which Chebyshev interval in which 88.8% of the data will fall within. So let's look at our little chart. 88%, actually it probably should be 88.9%. I think I just made a little typo there. There's 3 standard deviations of the mean. So we're going to do 525 minus 3 times 30, and 525 plus 3 times 30. Ends up being 90, so that would become 435. Add 90, we get 615. So that would be between 435 to 615. Just make sure you write the smallest number first. All right. Now the next one is phrased slightly differently. It says what percentage, so this time we're looking for the percent, is going to fall within this range. All right. So how we're going to figure this out, the easiest way is to start with the mean of 525. And we basically got to figure out how many times we've either added or subtracted the standard deviation. So what you could do, multiple ways you could approach this, is let's say you can just keep adding the standard deviation until you get the upper. So you add 30, it's one time, you get 555. That's clear, not it. So you do 555 plus 30. That gives you 585. Nope, that's not it. 585 plus 30. That gives you 615. That's not it. 615 plus 30. It is 645. Not it. 645 plus 30. And that gives you 675. So I added 1, 2, 3, 4, 5. So this would be 5 standard deviations. Let's see what that percentage corresponds to. So 5 standard deviations corresponded to 96% of the data. So we can say 96%, sorry about that, 96% fall within that range, 5 standard deviations. All right, you are going to have a little assignment over this, and I'm going to do the first problem on that together with you. Let's go ahead and take a look at that. And I'll probably actually might just delete this problem out. We'll see. So we've got a series of problems here using this theorem. And the only difference in these problems is that the data is going to be given to you as simply raw data, and you have to figure out what the mean and the standard deviation are. So when you do this, use 1var stats on your calculator. Definitely do that. Don't try to calculate the standard deviation in another way. Use the 1var stats function on your calculator. Remember how you do that is you do stat. So if you need to write this down, you do stat, and then you click enter on edit. You type all the numbers into list 1. I already did that for this one. Make sure you typed in the same number of numbers that are up there. You then hit stat, go over to calc, and then hit enter on 1var stats. Make sure the list matches list 1 or whatever list you typed it in. Frequency list should just be empty there, and then just go down to calculate. And we get on this one an x bar. I don't know if I can write x bar. X bar equals 72.68. And our sample standard deviation, S, is equal to 18.16. All right, so then what we're going to do for each of these is calculate the intervals it tells us to. The first one is 75%, so that means plus and minus 2 standard deviations. It won't let me write on here, so I'm just going to type it out. So 2 standard deviations, you don't have to necessarily write that. So I'm going to take 72.68, and I'm going to subtract 2 times 18.16. That gives me 36.36. Don't worry if you're rounding slightly different. It doesn't specifically say, so generally good to keep 2 decimal places. And then I want to add 2 standard deviations as well. So I start with my mean, 72.68 plus 2 times 18.16. And I get 109. If I want to do the 88.9, very similar, except if you forget 88.9, that's 3 standard deviations. So check that. So I'm going to be adding subtracting 3 times it. So I'm just going to stick with 72.68. And this is what I'm just typing in my calculator. Minus 3 times 18.16. Figure out what that equals. It gives me 18.2. And then do the same with a plus and calculate it there. So our 8 is going to be 18.2, comma, change it to a plus sign, and we get 127.16. All right. Now the last one, I think you actually would end up getting a negative number for this because it's 96%. So when you do this 96%, because it's 5 standard deviations, so I'm going to be doing 76.68 minus 5. Make sure you use in parentheses when you do this, times 18.16. When you do that, you are going to get a negative number, I believe. Yep, negative 18.12. However, think about the context of this problem. We're talking about the total number of hurricanes reported globally in this scenario. Well, you can't have negative 18 hurricanes. So when you write this, you don't actually want to write negative 18. You actually just want to write the lowest possible number, which is 0. And you're still going to have your upper bound will still be fine. The upper bound on this one is still going to be, let's see, it's 163.48. So what we're saying in all these, let's just say this last one, is on any given year, I could expect between 90, let's say we have 100 years. Well, I would expect 96% of them, or 96 of those 100 years, to have between 0 and 163 hurricanes. We would expect 96% of the data to fall within that range. All right, and again, we don't want to write negatives ever because you can have a negative hurricane. All right, so that basically does it. You have a few more problems on this to do. Again, make sure you're doing the 1var stats for this, and then just looking at whatever corresponding interval you need to do. And as always, reach out to me if you do need some help. Thanks.